Great. Thank you so much for inviting me today. And great to see so many friends and colleagues. And let me start with a disclaimer and a spoiler. The disclaimer is that I'm not an economic geologist. So I heard already that like a few people here are really interested, like knowing more about some deposits. And I am afraid that many of you know a lot more about the actual ore deposits, mineral deposits than myself. What I do try to do is to look at plate tectonic patterns. So I hope that it will make sense. The spoiler is that there are, as many of you know, there are no big, giant mineral deposits in the New England Orogen. There are a lot of small deposits, but none of them is a really huge one. And maybe there are none to be discovered that are really giant ones. And we will see the reason for that. So let's start. I will start with just a kind of a general introduction to the New England Orogen. We are sitting now in the middle of the New England Orogen on a Carboniferous accretionary complex here in Brisbane City. And it is constitutes the easternmost part of the Tasmanides, Phanerozoic, Eastern Australia. It is also the youngest portion of the Tasmanides. And it records a long-lived subduction environment. So the New England Orogen is a subduction-related orogen. It experienced subduction processes for a very long period, maybe 160 million years or so, and situated on like on the margin of Eastern Australia, of Eastern Gondwana. You know, perhaps not unlike the Andean margin. It's been described as an Andean type continental margin orogen. It experienced periods of orogeny, the so-called Hunter-born orogeny in the Permo-Triassic. You can see it here in the context of all the different orogenies in the Tasmanides. The youngest portion of the Tasmanides, the youngest phases of contractional deformation. So it seems to be the kind of right environment, you know, Andean type environment for the development of major ore deposits. And if we look at the Andes, this is just an image of the central Andes. We can see that there are a lot of similarities. So it is a curved subduction system. We can see that the subduction zone itself, the trench, is curved, forming the shape of the Bolivian orocline. It corresponds to a volcanic arc. We can see that the volcanic arc is, this is the present day volcanic arc. It is segmented. And so there are gaps in the volcanic arc. And it also creates like interesting kind of kinks and shapes in the kind of a long strike continuation of the arc. And we actually think that these kind of anomalies in the arc behavior play a very major role in the development of large porphyry systems. So, you know, separately, I will not talk about that today, but we have a project with Teresa Ubide and students working exactly on that, on whether these kind of anomalies, these kinks in the subduction zone and these kinks in the volcanic arc and associated subduction zone are actually porphyry kind of factories or areas where we get some anomalous magmatism and anomalous development of porphyry systems. So there are a lot of porphyry systems in the Andes. We all know that. Some of them are giant ore deposits. And if we compare that to the Permo-Triassic New England Orogen, That's from a paper that we published with Abbas last year. We can see that there are a lot of similarities, at least in the way that the arc looks. It's curved. A curved arc looks kind of similar, more or less the same scale also as the Bolivian orocline. The segmentation, I don't know if it's filled. It's just covered by the Morton Basin here, the Clarence Morton Basin. So I don't know if it's segmented or not. But it also has these kind of interesting kinks. So, similar kind of things to what we saw in the Andes. And there are porphyry systems in the New England Orogen. There are a few. But if we look at the actual metal endowment, we can see that there is a massive difference, of course. So I took this data from the USGS database for porphyry system, and we can see that there are 139 copper porphyry deposits listed for the Andes with an ore tonnage of 137,000 million metric tons. And the same database lists 10 deposits in the New England Orogen with ore tonnage of 85 million metric tons. So that's less than 3 orders of magnitudes compared to the Andes. I put here a combination of the New England and Lackland, so Cadia and North Park as well, just to show for comparison a lot more, of course, with those big deposits, but still not comparable in metal enrichment compared to the Andes. So what is the reason for that? Is there like a fundamental plate tectonic reason that controls whether large mineral systems are enabled or disabled? So that's the kind of question I would like to address. And before we do that, we can think about how we form large porphyry deposits. So I mentioned before, I'm not an economic geologist, but I know a thing or two about porphyry system and epithermal system. We need to have thick crust, right? So we need to have a thick crust that allows like a garnet fractionation, for example, is obviously very helpful in the development of porphyry systems. We need to have, we commonly have multiple ore forming events in a rich metallurgic system. So here's an example from the Andes, and the site of some of those giant ore deposits, neogen ore deposits, are also the site of much earlier deposits, as we can see here. So what is that? Permian and Cretaceous. So much earlier deposits. So it seems that the system is already kind of it's already fertile. It's already pregnant with all these metals, and just waiting for them to be stored. We need to have copper-rich magmas and fluids and reactive host rocks. So that's the kind of questions that we address in the project with Teresa. How to form those, copper-rich magmas in an arc system. We need to have structural focusing. So contractional events, for example, are very helpful in kind of localizing mineralization. And we need to have, and these are the things that kind of more relate to the kind of things that I'm doing. With many large porphyry systems and epithermal systems, we see that there's also a major tectonic change. So, for example, sudden change in convergence rates, faster convergence, larger deposits, slab tearing. We've been working on that with Jack Ward in his PhD project, and we showed here that in Sumbar, for example, in Indonesia, and other large porphyry deposits in Indonesia, we have kind of corresponding anomalies in the slab, some sort of tears in the slab, so some relationships there. And ridge subduction and flat subductions are two kind of major tectonic changes that have been discussed a lot in the literature. And just because I personally worked a little bit on ridge subduction many, many years ago, I will show you that example. And these kind of parameters are all interlinked, of course, right? When we can have ridge subduction, we can create a slab tear, and we can also flatten the slab. So just an example from, again, from the Andes, showing those aseismic ridges that are subducting beneath the Andes, the Nazca Ridge here, Juan Fernandez Ridge, there are others as well. And they correspond to a flat subduction. Yes, so here we can see that we have the kind of segments of flat subduction. The active arc is the arc is inactive in the areas of flat subduction because the slab is too shallow, is flattening at 100 kilometer depth, basically destroying the mechanism for the formation of the arc. And we can see that mineralization, that these are the largest porphyry deposits in the Andes that are younger than 18 million years, so concentrating only on the very young deposits. We can see that they overlap perfectly with the areas of flat slab. So people have suggested that the flat slab is a mechanism for ore formation, that particularly the transition to flat slab is really important because it corresponds to a process of contractional deformation. Flat slab creates more coupling. There is more contractional deformation. It corresponds to arc migration. The arc can migrate to to form kind of new, like much more distal kind of focus and flare up at the end of volcanic cycles. So all these kind of things were linked to ore formation in the Andes and elsewhere. And I did a little exercise just when I finished my PhD, so more than 20 years ago, particularly on this part of the Andes in Peru. I just looked at all the mineral deposits that I was able to kind of put together, and thought, like, are they actually linked also to the Nazca Ridge, or is the Nazca Ridge related to the flat slab, which is related to the mineralization? And the answer is not very clear from that kind of snapshot, right? So we saw that the whole segment of flat slab has mineralization associated with it, but not necessarily corresponding to the Nazca Ridge. So what I did, just the kind of deposits that we have here, we can see that temporarily we have kind of a pools of metal enrichment, metal endowment at around 15 million years. So something is going on at that time temporarily. And what I basically try to do is to integrate that in a reconstruction and see whether the ridge itself plays a role in mineralization. And to do that, I did I looked at the Nazca Ridge here and compare it to what we see on the other side of the East Pacific Rise. So it is a kind of an oceanic plateau that forms at the spreading center, and therefore it has a brother or a sister here on the other side of the Pacific Ocean. And we can actually know what was the shape of the Nazca Ridge prior to subduction from this part, the Tuamato Plateau in the Pacific Ocean. So here's the Nazca Ridge. I got the idea of do that from the work by Andrea Hampel. And what I basically did is just taking the mirror image of the Nazca Ridge and integrate that in a reconstruction. So here is the Nazca Ridge before it got subducted. And actually, when we do that, we can see that there's also the Austral Plateau here, which has a brother that got completely subducted in the Andes. So sorry, the Marquesas Plateau, and the Austral Plateau is this one, the Iquique Ridge. So we can do the same exercise for all of them. And when we integrate that in a reconstruction, we can do some plate kinematic calculations just with the plate circuits, Nazca plate relative to South America. And we can see that there are some ore deposits that are older. We already mentioned that There are many older ore deposits in the Andes, but they become really dominant once the Nazca Ridge starts to subduct. And because of the angular kinematic relationships, the Nazca Ridge actually going to hit way north to where it is today. It's kind of sweeping southward along the coast of Peru. So here's the Nazca Ridge, here is the Inca Plateau, the other one that we saw in the image before, and we can see that once it hits the trench, then there is a huge concentration of ore deposits associated with that. So, and similarly here with the Inca Plateau. So we see those kind of relationships, and that also explains why the area of flat slab is 500 kilometers and not just the width of the Nazca Ridge. So that's the exercise from Peru. I then did the same for the Juan Fernandez Ridge in Chile, and we can see again, we can bring back this hotspot track, and we can see that it arrives at the subduction zone again way north of where it is today, corresponding to the earlier kind of mineralization here, and kind of migrating southward as ridge subduction moves to the south. So yeah, just a kind of an example of these kind of tectonic changes that we are dealing with, and with that in mind, we can go and look at the New England Orogen. So kind of working on the New England Orogen for many years on different aspects of the tectonics of the New England Orogen, particularly the oroclines in New South Wales, but then I started working more and more in Queensland as well, the Gympie province, and further north. I started to be curious on the kind of spatio-temporal patterns in mineralization. And I decided to do a simple exercise. It sounded very simple. When I thought about it, it became, of course, a nightmare in terms of compiling all the data together. I opened the Australian Mine Atlas, the GA's Australian Mine Atlas. Here are all the mineral deposits. And I filtered the deposits to operating and historical mines and other known mineral deposits. And I looked at those commodities. So, of course, most importantly, copper, gold, silver, moly, zinc, tin and tungsten, and antimony. These are really the important ones. And I excluded some deposits that were placer and alluvial deposits. I excluded also the post-Triassic deposits because they are not clearly linked to this kind of subduction history that we're going to see in the reconstructions. And that resulted in a database of 116 deposits. So here they are. And I also downloaded just mineral occurrences for all these commodities. And so we have a huge amount of gold occurrences. We have much less, I don't know, moly occurrences or whatnot. But that allows me to create some kind of heat maps, and recognize perhaps some patterns. I will use some of those maps later. So then I started looking at all the possible information on any of those 116 deposits. So obviously, starting with the published literature, some deposits been studied a lot. Most of them were never kind of do not have a single published paper on them. So I moved to those excellent reports by the government, both the Queensland and New South Wales government. They were an excellent source of information. I looked at books, at theses. I looked at exploration reports, and even ASX announcements. So each one of those always have a little bit of information on the geology just from the geologist in who explore the area. And that allowed me to classify the deposits into 5 groups. So the first ones were ultramafic related deposits. The second group, so basically thinking about the mineralization style, it also allowed me to constrain the timing of mineralization. Well, I did as much as I can to constrain the timing of the formation. I did not do that for the ultramafic related deposits. Most of them are laterite deposits, but for all the other groups of deposits, I attempted to put some constraints on the mineralization based on, sometimes really excellent constraints, direct dating of mineralization using audiometric dating, and sometimes very, very kind of poor constraints on just field relations or proximity to a possible intrusion that is responsible for mineralization. And that this uncertainty is expressed in the error bar. So intrusion-related deposits, porphyry deposits, basically other intrusion-related deposits. The fourth group are epithermal and VMS deposits, and the fifth group are the orogenic deposits. These are some of those where the most difficult ones to get any information on the timing of mineralization, so leaving an error bar that is almost kind of makes the age almost meaningless. So with that in mind, let's go and now look at the geological context of those deposits. So the New England Orogen has, as I already mentioned, has ultramafic rocks in some rare ultramafic rocks, but very important to its geological evolution. So these ultramafic rocks are, at least in some places, clearly associated with dismembered ophiolites. Sometimes they occur with gabbros and plagiogranites. They are quite extensive in Marlborough. They occur also along the Great Serpentinite Belt here in New South Wales. And in some places, it's been shown that they are the oldest components in the New England Orogen. So the ages of some of those plagiogranites, for example, is Cambrian, so way older than anything else in the New England Orogen. Other ages are younger, Devonian ages, maybe even Permian, so different kind of context. We're working actually on those rocks in the scope of an ARC linkage project, jointly with the University of New England, Luke Milan, with QUT, with Balz Camber, and GSQ and GS New South Wales. And Julius, who is here, is our PhD student working specifically on the ultramafic rocks. Gabriel is based in New South Wales and working mainly on the Great Serpentinite Belt. So these are the ultramafic rocks, and they are commonly found adjacent to other relatively old rocks in the New England Orogen. These are early Middle Devonian rocks that are arc-related, volcanic clastic rocks, relatively primitive in composition, so more kind of mafic in composition. They've been described as island arcs in the past. They are found here in Queensland, Calliope province, in southeast Queensland, Silverwood, and northern New South Wales, and in New South Wales, England Orogen terrain. And Igor, who is here as well, is working is doing his PhD on that topic, sponsored by the Bryan Foundation. So those rocks, the ultramafic rocks and those Devonian arc-related rocks are spatially kind of linked mainly to a major tectonic contacts, the Yarwell Fault here and the Peel-Manning Fault in New South Wales. Not exactly, but kind of we can see the spatial relationships, and together they kind of delineate the shape of the oroclines. So these are the New England oroclines. You can see we could imagine them just by kind of doing the continuation of the ultramafic rocks, but we can see them very clearly if we look at the aeromagnetic image, for example, for Southeast Queensland and New South Wales. So these are the oroclines. We will see them again in the reconstructions. The majority of the rocks in the New England Orogen are late Devonian and Carboniferous arc-related rocks, so supra-subduction-related rocks. Those rocks that we see here in Brisbane. So there are arc and fore-arc in particular. So we have the arc exposed here in Queensland quite extensively. A little bit of exposures of the arc also in New South Wales, and we have the fore-arc divided into an accretionary complex in the east and a fore-arc basin to the west, separated by those tectonic contacts that I mentioned before, the Yarrow Fault and the Peel-Manning Fault. So there is some kind of later restructuring of the fore-arc basin against the accretionary complex, and altogether, it kind of gives us an indication of west dipping subduction zone. And if we look in present-day coordinates, we have the arc, the accretionary complex, the fore-arc basin on top of it. And again, if we look at the kind of the bedding, the fabrics, different features within those, just kind of putting all those units back together, we can see that they delineate the oroclines, basically telling us that those units got rotated and translated after they formed, so sometime later. And we think, based on a lot of work that we did in particularly in New South Wales, is that the timing of oroclinial bending occurred during the early Permian. Actually, even though these are kind of mega faults, they actually form by back arc extension, by translation of and rotation of blocks because of the space formed by extension. So the early Permian, we can see here, early Permian features, the Boyne Basin, Gunnedah Basin, Sydney Basin, and the additional basins within the New England. They are all extensional back arc basins. That's their interpretation. There's also a lot of magmatism associated with the basins, maybe this kind of gravity ridge that we see here in the Boyne Basin perhaps indicates some mafic magmatism at the base of the Boyne Basin. S-type granitoids here in the southern New England Orogen, more granites here, and volcanics that are all bimodal volcanics that are all kind of are associated with an extensional back arc setting. So that's the early Permian. And later on, from the middle Permian to the Triassic, we see a lot of felsic magmatism, particularly I-type granitoids, with a major peak in magmatism at around the Permian-Triassic boundary 250 million years ago, basically telling us that we are back in the arc. So we see those migrations. We were in a back arc, and now we are back in an arc system. And during that period, we also have those pulses of Hunter-Boyne deformation. And they occur in pulses. It's not continuous deformation. We call them Hunter-Boyne 1, 2, 3. So kind of first, like onset of Hunter-Boyne in the middle Permian, then the second stage of Hunter-Boyne orogeny, and the final stage at around the 235 to 30 late Triassic. And Yan Xiong, who is here, is doing his PhD mainly on the Permo-Triassic belt. So it looks easy. You have very simple plate tectonic history of the New England Orogen. Here is the New England Orogen. This is what we see between those lines. We see that in the Devonian Carboniferous, we are somewhere in the arc, fore-arc. Then we get obviously kind of trench migration, and we are in the back arc in the early Permian, and then we are back in the arc in the Triassic. So looks easy, but of course it's way more complicated. We're still scratching our head how those ophiolitic remnants got in place. What is the meaning of those early Devonian, early middle Devonian arc-related rocks? We see that we keep getting, even in the Devonian Carboniferous periods of advance and retreat, we have the oroclines, which really mess up the whole kind of the whole geometry, and we get those pulses of deformation in the Hunter-Boyne orogeny, intermitted by even periods of extension. So let's now move to the actual deposits. So starting with the ultramafic related deposits, actually I haven't done much in relation to those, except of kind of putting them on a map and kind of link them to the shape of the ultramafic belt that we have here in the New England. Most of them occur in the largest kind of extent of exposure of ultramafic rocks around Marlborough. So mainly laterite, nickel laterite deposits, and but we also get podiform chromotite, for example, here in Bayulgil Massif in northern New South Wales, and we also get gold mineralization associated with silica carbonate alteration. So some of those were linked kind of to orogenic gold, but the interactions with the serpentinite is what allows mineralization. So moving to epithermal and VMS deposits. So during the Devonian, so I'll just show kind of snapshots of different timing, because now I think that I have some idea on the timing of each deposit. So when we look at the Devonian, we have only two deposits. One of them is very important. The other one I think is not so important. Mount Morgan, a very important mineral deposits, reasonably large one, and the oldest one in the New England Orogen. So possibly linked to this middle Devonian arc that Igor is working on. So we can see this Calliope arc here in blue. So that's Mount Morgan. Zelma, I'm not so sure about it. Based on what I learned from reading on Zelma, it seems to be directly linked to the actual volcanism, the Campwin volcanics in around Sarina here in northern Queensland. But so if so, then it's a late Devonian kind of late Devonian VMS deposit. However, it could be a younger deposit, maybe even a Cretaceous deposit. There's a lot of Cretaceous granitoids in the area, so maybe the other ones were mineralized. I kept it as like tentative as a Devonian deposit. So looking at the younger deposits, we can see that this is really when a lot of mineralization is happening in terms of epithermal deposits. So really the bulk of epithermal deposits in the New England Orogen occurs in the early Permian. So kind of seems to be, both spatially and temporally related to the extension that created the Boyne Basin. They occur at the margin of the Boyne Basin, related to some of those volcanics that sits at the base of the Boyne Basin. So Krakow Golden Plateau, for example, very important deposits are part of that epithermal belt. And then younger epithermal and VMS deposits, there are only few. So really the majority of the epithermal deposits are early Permian. We find some younger ones in the late Permian, New South Wales, Mount Carrington, for example, related to Drake volcanics, and the gold fields around the Barrington Tops. So these seem to be related to a back arc in New South Wales at that time. Then we have deposits like Silver Spar, for example, that are sitting in the back arc in the Middle Triassic. And then we have a few deposits that sits in the back arc and arc in Southeast Queensland during the late Triassic. So the important message is that the epithermal deposits are mostly back arc. From my kind of point of view of tectonics, that is really the major finding. Let's move to porphyry deposits. So there are only few porphyry deposits, and they only occur in the northern New England Orogen. I think the database, the USGS database, had one in New South Wales as well, but to be consistent, I kept only those deposits that were listed in the Australian Mine Atlas. So this is why you can see the discrepancies in my slides. So here are some of the porphyry deposits in the northern New England Orogen. They occur here in a kind of copper moly belt. And it's actually interesting the way that they're kind of spatio-temporal occurrence, because from the work that we did last year, kind of mapping the evolution of the arc through time in the Permo-Triassic, we were able to see that that the segment here where the porphyry deposit sits, linked to that kind of arc segment in time, is the segment that was subjected to arc advance, creating this kind of kink in the magmatic arc. So there are some interesting kind of spatial relationships, and our conclusion, based on a number of additional arguments, was that this arc sector is sitting on a somewhat shallower dipping slab, on top of a shallower dipping slab. So, kind of rings a bell to what we saw in the Andes. So these are the late Permian to middle Triassic porphyry deposits. Moving to the late Triassic, we see a number of additional, just a handful, 4 additional deposits and porphyry deposits. And the difference is that they are mainly copper gold deposits. From copper moly, we move to copper gold, and they sit pretty much within the what we inferred as the late Triassic arc. We can see that if we put the copper occurrence on top of that, we can see that perhaps the map of total copper occurrence actually is linked to that late Triassic belt. Moving to intrusion-related deposits. So intrusion-related deposits we can find in the northern New England Orogen, just very few in the Permian, and a lot more in the late Triassic. For example, Mount Rawdon, one of the largest gold mine in Queensland. And they form kind of a coppery gold belt, intrusion-related belt, and corresponding to the porphyry belt that we saw before. And if we put the gold occurrence, we can see again that perhaps there is some link here. And if we move to the southern New England Orogen, we find a very different kind of situation. In the southern New England Orogen, we find very few early Permian or middle Permian deposits. We find just a couple of late Triassic deposits. The majority of the deposits are again kind of late Permian, early Triassic, around 250. Similar to in timing to what we saw in the northern New England Orogen, but in terms of type of deposits, of commodities, we see that they are dominated by tin, tungsten, some silver, arsenic. So a kind of a different type of mineralization linked to the granites within the arc. You can see the shape of the arc here in the dashed line. So that is the contemporaneous arc. And if I put the heat maps, this one is for tin occurrence, we can see a perfect match with the Stanthorpe here as well as the continuation of that. So that was the intrusion-related deposits, and finally the porphyry the orogenic deposits. So the orogenic deposits I mentioned before, they are difficult to understand when exactly they formed. So some of them are really poorly constrained. Others are better constrained and do show relationships to Hunter-Bowen phases of the formation, which kind of makes sense. So we have Bingara, for example, Nandel, Hillgrove as well. that are linked in time and also in space here to Hunter-Bowen 2 structures, so 250. And we have Gympie goldfields, for example, where we have a lot of gold. This is 27 kilogram of a nugget. And that occurred at the terminal stage of Hunter-Bowen orogeny at 230. So these are the orogenic deposits. And the last thing I'm going to do is to put that in the context of plate tectonic reconstructions. So there are a lot of uncertainties in the reconstruction. Once you start drawing those reconstructions, you put yourself in trouble always. But it's a good exercise for recognizing, problems, recognizing what could have happened, and testing those hypotheses. So what I did is taking the Australian continent and moving it on G plates with reconstruction by Matthews and others. It doesn't really make much difference except of changing the coordinates. So you will see that we are mostly in much higher latitudes here. And then using all the different constraints that we had over years of work on the oroclines and on the basins and whatnot. We did some palomagnetic studies and of course other published information as well. So starting with the late Devonian, this is where we know least. So the late Devonian, there is actually quite little information we can get from the New England Orogen itself. We know a little bit more from the Lachlan Orogen on the Bega batholith, for example, which was then the site of Bacchac extension later on. So some indication for trench retreat here, indication for trench retreat also in the latest Devonian corresponding to the Drummond Basin here. And the important thing as far as the mineralization is concerned, that this is when Mount Morgan forms a little bit earlier than the snapshot that we see here. So it is this remnant arc that we see here in blue, and maybe Zelma as well in the late Devonian arc. So that's really all I have to say about the late Devonian. Moving to the Carboniferous, we can see here the pre-oroclinal shape of the plate boundary. Again, big assumptions. We don't know that for sure, but we know that the oroclines did not yet form. And really, I put those orogenic golds here. They have a huge error bar. I don't know what their timing. They occur in the accretionary complex, in the Carboniferous accretionary complex. So, they might as well stay here, but they could be younger. The important thing maybe is what we don't see here. We don't see any mineral deposits apart from those suspicious orogenic gold. We don't have porphyry deposits. We don't have intrusion-related deposits. Maybe the system is barren. So that is interesting by its own right. Maybe it's a matter of preservation. This arc here is mostly eroded. We find mainly deeper sections of the granites. Those arcs here are really mostly covered by the Sydney and Gunnedah Basin. So, if the arc was more fertile, maybe we don't have access to it. Moving to the early Permian, this is when the oroclines form. We envision that they form by asymmetric retreat, something a bit similar to what we see in the central Mediterranean, for example, or eastern Indonesia. And we formed the oroclines during that period. The important thing as far as mineralization is concerned is that in the northern New England Orogen, we have this epithermal belt that is actually one of the most prospective belts in the whole of the New England Orogen. So the early Permian is important, particularly in the northern New England Orogen. Moving to the onset of the Hunter-Bowen orogeny, so the first contractional phase apparently did not do much to localize mineralization. Here we see barely any mineralization. We know that that is the timing when Hunter-Bowen kicked in from those disturbed sediments that we find. So the rising topography creates those mass deposits. we dated that. We know that happened at 270, but no major mineralization. And really, when a lot is happening is during the second phase of Hunter-borne orogeny. This is the phase that is accompanied by a lot of magmatism, almost like a flare-up in magmatism. We can see that both in the southern New England Orogen, and we see that also in the northern New England Orogen, a lot of magmatism concentrated around 250 million years. And at this time exactly, we also get some of the largest metallogenic belts in the New England, the copper moly belt in the northern New England Orogen, and the tin tungsten belt in the southern New England Orogen. And finally, the late Triassic, so the final stage of Hunter-borne orogeny, we can see that we do have kind of metallogenic belt only in the northern New England Orogen. And the reason for that is that the northern New England Orogen sits within the arc. At that time, it is subjected to contraction and deformation, while the southern New England Orogen sits mainly in a back arc region. So not so good for intrusion-related mineralization. So just summarizing, kind of concluding, and that will be my last slide. We have 4 major metallogenic belts in the New England Orogen, extension-related epithermal belt in the early Permian, copper moly belt in the early Triassic, in the northern New England Orogen, while in the southern New England Orogen at the same time we have the tin tungsten belt, and the late Triassic gold-copper belt in the northern New England Orogen. And the question is, where are those giant porphyry deposits? The same kind of diagram that I took from Richard's paper on large copper deposits. And I guess we need to ask ourselves, did we tick the boxes for the formation of large copper deposits? And the answer is that we ticked some of them. So the New England Orogen does have some of the ingredients that we need for large copper deposits. We see a tectonic change, like the shallowing of the slab dip angle that seem to actually control the sites of mineralization in the northern New England Orogen. We see that we have multiple ore-forming events, so same mineralization occurs again in different magmatic cycles, particularly in the Permo-Triassic. And we have structural focusing associated with Hunter-borne orogeny. But it seems that some of the things are missing, and particularly the fact that we never really manage. So, you know, maybe we don't have sufficient metals in the magmas and fluids, and that might be related to the fact that the crust never really manages to become thick enough. And the reason for that is that it's an environment that was repeatedly subjected to changes between trench advance and retreat. So every time we have those periods of trench retreat and extension, we basically destroy everything that we produced. So perhaps that is the major reason that we can't form a large, like really large porphyry deposits. And that's all. I leave it here. Thanks a lot.
Any questions? There must be. And over there.
Thanks, Gideon. I'm wondering if the inflections in the dip on the slab, how do they relate to, say, beavers, some of those really big transform features that from the failed rift? Is there any relationship between the positions?
I'm not sure. I don't know. Weaver's diagrams are so dense and complicated that as far as I know, there's no lineament that correspond to that change that we saw in Southeast Queensland. But now when you say that, it's worth checking some of those diagrams, because you're right, there are major lineaments, and you expect to have those kind of origin perpendicular structures or origin oblique structures in association with those with those changes. So yeah, good point.
When seen graphs about the forces, I was wondering if the patterns that is have been compared with the Andes.
Say again, I didn't get it, sorry.
If the patterns element forces with the timing that the timing gap is similar to the pattern of the comments.
So you ask if the time gap is comparable to the Andes?
If the patterns in the Andes is similar, just transposed to more recent timescales.
Yes, I mean that essentially the point that I tried to make in the first kind of example that I showed from the Andes, that the space and time scales are absolutely comparable. So the map of the Central Andes was pretty much the same scale as the map of the whole of the New England, and the time scales are kind of comparable, I think, in terms of long-lived subduction zones and the cyclicity in magmatism. So I guess the major difference is that the Andean belt was not subjected to the like to those repeated periods of trench retreat. So trench retreat is not good for mineralization.
Yeah, which yes, that's okay.
You? No, that's on the market. Is there another one down here? Oh, that's right. Give us lights a little bit.
Amazing talk, Gideon. Thank you. I was thinking of the analogy with the Andes and how you don't get the big porphyries in Australia. In the Andes, you can use geochemical indices to assess crustal thickness or metal enrichment in magma, like if the magmas are more arachitic or whatever. Is there any information on the geochemistry of these magmas and if they vary along those kinks in Eastern Australia?
Yes. Yeah, I have to admit that personally, I haven't done much yet on the geochemistry, and Xiong starts to deal with that. The group at QT, Dave Gast, have worked a lot on kind of spatial temporal variations in the arc systems, and and sooner or later we should kind of try to compile it in a similar way that we did for the Andes. It's going to be more complicated because the rocks are mainly granitoids. So so it would be more difficult to get kind of the more original signature on on melting that that you can get in some places in the Andes. But there's a lot more to be done.
Excellent. Don't have to go too far.
I don't know much about this, but there's the overriding continental volcanic arc there built upon Precambrian basement on Craton, whereas this arc is only one in the long line of the entire Tasman Rise. It's built on top of other accreted crust. You've got the Lachlan behind it, and the Thompson Fold Belt, and the Kamen-2, and so on and so forth. So I'm wondering if that might have something to do with the nature of the source materials, not as being as primitive, having been cycled many times, and also not getting the thick crust.
Yeah,
Because that's
exactly.
a big difference.
think
Because
yeah, both.
it's the most outboard of many accreted slices. I don't know about the Andes. It's the first one that's bolted onto the craton.
Yeah, no, in the Andes you do get superposition of crust of different ages in the same place. So it is a much better recipe, I would think, for for mineralization, and of course a way to build a really thick crust. So you get to a 75-kilometer crust in the Andes. So in the New England, as you say, the problem is that it's part of the Tasmanides. If you think about Tasmanides, it is a long history of subduction, but it's stretched over like a huge kind of width, across the Orogen. So it's basically kind of, you are unable to actually build, a really thick crust and kind of capitalizing on whatever you have already in the crust in order to form, to enrich in metals. But that also, with that in mind, we should also ask ourselves why Cadia and North Parks are so have so much gold in them. So
but they're still not the same scale as the big Andes deposits. I mean, they're big,
yeah,
still not quite big. One of the specific diagrams you had up was during the Carboniferous, where you showed the Carabubular Arc and the Tamworth Belt, the Tablelands complex, and you had on the far western side a thing called BG, but it wasn't explained what that was. Is
the Bathurst granite.
So it's a name.
Bathurst.
Oh, Bathurst granite.
Yeah. Yeah, so it's not part of the New England kind of part of the geography of the New England, but it is it is 340 to 320 arc-related granite, and so corresponds perfectly to the arc of the arc that sits adjacent to the 4 arc regions that we see in southern New South Wales. And within that granite, you actually see kind of evidence of arc migration. So actually the 340 ages are the most distal ones, and then you see that it's kind of migrated eastward, so basically indicating that the trench is retreating during that time.
That's very strange because it's running east-west and all the other ones.
Well, it runs east-west, but it changes through time. So it's actually kind of, it's like a hotspot track. It kind of gives you the location of the arc through time.
Because there is a ridge underneath the Carabubular Basin called Bogaboy Ridge, which is just at the back of the Carabubular Park. But I don't know if they know a lot about Egypt or anything, because maybe that's a candidate for somewhere to come. It seems to be a candidate for where you might get a porphyry, and yet there are none.
Yeah.
It's strange. All right.
Back to you, Doug. Yeah, just following on from Doug's discussion there, the other major difference between the New England and the Andes is age.
Oh, yes.
And is there any indication that the material that's being subducted in the case of the New England is less evolved than what's being subducted today in the Andes?
Yeah, I mean, I don't know what was subducted. That's the biggest problem that we have in this kind of destructive environments. That I made a big deal on ridge subduction. I would have no clue whether you had something like that in the New England, because you destroy the evidence. So so I don't know what really was subducting. The only thing is that we can infer that maybe there were, if we see that we have evidence for flattening of the slab dip angle, then you can think, maybe some, more buoyant material arrived at the subduction zone or whatnot. But I wouldn't know the answer to that.
We've got a couple of questions from home. Mike asks, what drives the slab retreat in the New England Orogen?
So I guess what drives slab retreat in general is the negative buoyancy of the oceanic lithosphere. So slab retreat actually is the norm rather than the exception. You have oceanic lithosphere, which is denser, colder, heavier, and it is basically it basically, as we all know, it's doomed to be recycled. And as it does that, it has a component like a vector component that is also kind of pushing it backwards. So it's not only downwards; there would be a component also backwards. And that's the reason that most slabs are subducting. And I guess the interesting question is why there was a lot less retreat in places like the Andes.
Thank you. And question from Lyle. What part of the crust is being rotated about a vertical axis on your orocline model? And does orocline formation require decoupling at one or more crustal depths and or at the moho?
So the way that I think about it is using modern analogs for orocline formation, so particularly the Mediterranean and Southwest Pacific and Eastern Indonesia, and you see that it's a whole crust process. It's a lot more than the crust. It's essentially a lithospheric scale process in which you retreat the slab, the trench is retreating, and you create extra space in the back arc region. And to accommodate that space, you would have to have you would get obviously sedimentary bases. You can form young oceans as well, but you don't necessarily need to form a new ocean. You can thin the crust, and the material basically just get adjusted in the overriding plate, rotating and translating to kind of get adjusted to the new kind of configuration of the plate boundary. So it all boils down to plate boundary migrations. The boundaries are running away from from where they were, and the crustal material at the overriding plate needs to be basically kind of rearranged.